In this video, we're going to talk about a concept in sensitivity analysis with our pencil to production problem, and it's the concept of shadow price, or also known as dual value. And so just for a little bit of background, we were working on the pencil production problem, which is stated in this GitHub repository right here on this markdown page, where we're making two different types of pencils, an economy pencil and a deluxe writer pencil, and we're trying to maximize profit. And you can see in a previous video where we worked to develop this model and also solve the model. And so when we talk about shadow prices or dual values, we're looking for the amount of change of the objective function value when I start to play around with and modify the right-hand side values of my constraints. So you can see all these constraints right now are less than or equal to. And so it'd be saying things like, well, on the assembly one down here, which is the 18 hours, yes, if I start to mess with the capacity there and I give a little more assembly labor or a little less assembly labor, how much is that going to affect the objective function value? And you can see this would be a nice thing as a manager or somebody who's trying to plan production, if I had a little bit of variation of labor that I could then move around from one place to the other, that may be a nice piece of information to have. And so with that being said, let's go ahead and hop into this and kind of see a graphical approach to understanding what this concept is. And then we'll also show how you can find this value relatively easily inside of the Microsoft Excel environment. So first, just a little bit of recap here as I page down through my Jupyter notebook. We can work this out using a graphical solution method, seeing as there's only two decision variables, and that's the chart you're seeing here. Just assuming real decision variables here in terms of the quantity of economy writer pencils and the quantity of deluxe writer pencils to schedule for production, we end up with this feasible region here that's shaded in blue, and then we can start plotting objective function lines and find out that the objective function line will be maximum when it's intersecting the feasible region at this point, roughly 1,721 economy writer pencils and 5,102 deluxe pencils, and it'll yield a profit contribution of $5,008.31. And you say, hey, that's great. But then we ask the question, you can see the question down here that I am posing, by how much will this profit increase if we can secure one additional hour of labor in the assembly department? So another way of saying that is, well, if I take that 18 and make it 19, can I determine how much the objective function will increase without having to resolve the model? And it turns out you can if you have the ability to look at this sensitivity analysis and specifically the shadow price or dual value. Before we go straight to that, let's first look at this graphically. And so if I look at this graphically, what I'm doing is essentially growing my feasible region, right? Since I'm adding one more additional hour of labor, I'm actually growing the feasible region, assuming that that constraint is binding. In this case it is. If you remember from our previous video, this line segment here on top, if I remove this line segment here had to do with the shaping department. This was the assembly department, and this here is a line associated with the inventory of matte paint. So now when we add an additional hour of assembly labor, we're going to be growing and extending this line out in this direction. And that new area that we gain is what I'm showing in red. And so then we would start saying, okay, with the combination of the blue and the red here as my total feasible region, where's the optimal solution at? We will find that the optimal solution again remains at this point here, which is the intersection between the shaping and assembly constraints, and that would become our new optimal solution, which shows a total profit of $5,167. So we would say, okay, what the change is would be the difference between these two, right? The 5,167 minus that previous value, which was roughly $5,008. And that's what I've done here in the bottom of the screen, where I've just taken the difference and I found the value to be roughly $159.06 there. And so that value, since we made a unit increase, we went from 18 to 19, that 159.06 would be considered the shadow price, also known as the dual value of that constraint. And that's right here, the graphical interpretation. And it also would go the same effect if I was starting to decrease it as well. You would say that the objective function would be decreasing at that rate, assuming you haven't hit something called the range of feasibility. And so what is this range of feasibility, you might be asking about? Well, at some point, if I continue to increase this, for instance, that assembly labor goes from 19 to 20 to 21, 22, at some point I'm going to kind of saturate things, right? At some point I will end up with excess or a surplus amount of assembly hours that are going to be unused, and basically the assembly constraint will no longer become binding and another constraint will become binding. And in this case that does happen, and you can see that graphically as well. So now I've increased the assembly hours to this 21.538 hours, and this is the upper bound of that range of feasibility. The range of feasibility being the lower and higher limits by which the dual value can be applied. And so in this case, if we again continue on with the graphical method, I will go ahead and show that purple, and that purple constraint is the curing department's constraint. And notice here, this is where the curing department constraint is going to become binding at the point that we have 21.538 assembly hours. So if I continue to push the assembly hours higher, then we would start receiving excess time in labor for that department, and it wouldn't do us any good in terms of raising the objective function values further. And so hopefully that gives you a little bit of a conceptual view of what the dual value or shadow price is doing in our sensitivity analysis. But you also may be left with a question at this point of, I've just stated 3.538. How did I know that value? And the easiest way that I've found to do that is using Microsoft Excel's sensitivity analysis tools. And so this is the workbook that I have on GitHub that shows the solution to this problem using Microsoft Excel and the native solver inside of it. And when you run that solver, you have the ability to expose some reports at the end. It's very easy. It's just the dialog box that pops up where it says the solution is to be found, and then on the right hand side you can click different reports to show. One of those reports is the sensitivity report. And so this is the tables that show up for the sensitivity report. I believe this right here is our assembly constraint that we're interested in. And notice right in the body of this table, right on the row, it shows the shadow price that is 159.06 and change, if you will. And so that's the exact value we're looking for. And then also notice here we've got the allowable increase and the allowable decrease, defining the limits by which this shadow price can be applied. And again, we would call this the range of feasibility when I take 18 plus the 3.53 to get the upper bound and 18 minus the 3.14 to get the lower bound. And so Microsoft Excel makes it relatively easy to expose these shadow price as well as this range of feasibility. Other packages would also allow you to inspect these values as well. Just the syntax as far as what you may have to type in for using like GLPK would be obviously different, and obviously the format that it shows you may be different as well. And so hope that helps you figure out a little bit about how to determine the dual value, as well as also the interpretation of it with respect to the model.